This is a webinar which is intended to help you connect the graph motion with some of the kinematic equations and the actual motion of an object. And so the plan for this webinar is to practice and apply interpreting and creating graphs of distance versus time, velocity versus time, and acceleration versus time for objects that are moving in a straight line. And the reason I think this is important is because physics teachers like me tend to focus on algebraic representations of motion. So we spend a lot of time working with equations. We love equations. Um, but to be successful in the AP exam, it really helps to understand how to represent motion in graphical form. So the AP really values multiple representations. And so that's what we're going to focus on here. So during this webinar at any time, it'll be most useful if, when I pose a question, you take a second to pause the video and think about the answer. I will probably tell you to pause the video and then maybe make a sketch of a graph or something and then move on. So that if you just kind of watch it straight through and don't really participate, it's pretty boring, as is most of physics. It's not really a spectator sport, so it's more fun if you participate. So when possible, pause the video and think about it. Okay, so I think it's fairly well known at this point in your sequence in the course that if you graph position versus time, the slope of the graph tells you the velocity. And of course, slope is just the rise over the run. So if you take the rise, which is delta x, divided by the run, which is delta t, you get the velocity. Okay. So on a graph of position versus time, the slope of the line is the velocity. So if you have a representation like this, then you can tell that initially the slope is large, so the velocity is large, and it's positive. The object is moving to the right. During the next segment, the velocity is still positive, but it's not quite as big, so the object has slowed down. During the third segment here, the slope is 0, and so the velocity is 0. The object is at rest. And during the fourth segment here, the slope is negative, and so you can tell that the velocity is negative. The object is moving to the left. So just for fun, take a look at this graph and see if you can think up a story that maybe involves a furry mammal or a marsupial or whatever your favorite animal is. Tell a story about what's happening to the animal that is represented by this graph and try to include velocities and times in your story. So just see if you can make up a story about what's going on with a mouse or a platypus or whatever the heck it is you like. And whose motion is described by this graph. So pause the video, take a second to maybe type it up or write it up, and then move on. Okay, so hopefully you're back now. So during this first section, we can calculate the slope. The slope is the rise over the run. So it tells us that, first of all, it's positive. The object is moving to the right. This happens for a total of 15 seconds. We know that because it lasts for 15 seconds. And it's moving 0.33 meters every second. Okay? So just for reference, humans walk somewhere around 1 meter per second. So this isn't too fast. During this section right here, the object is at rest. And that lasts for 5 seconds. We can tell that because of the domain here from 15 to 20. And during the last section here, the object has a negative slope, so the velocity is negative. It's moving to the left. And it does that at about 1 meter per second. The slope is -1. So negative meaning to the left, 1 being the magnitude, the speed at 1 meter per second. And that happens for 5 seconds. So my story would probably be like a mouse comes out of his hole and he slowly ambles across the kitchen floor where he finds a piece of cheese. For 5 seconds, he nibbles the cheese, and then a cat appears. And so the mouse dashes back to where he started from much faster than he came out. So any kind of story that has those kind of components would be correct. All right, so now here we have a graph. It's position versus time, and the slope starts off small, but then the slope gets larger and larger again. And so in this case, we would say the velocity is increasing, and we call that an acceleration. So when the graph is curving, what's happening is there's an acceleration. The velocity is changing. The slope down here is not the same as the slope here. The slope is increasing. And so this graph is actually curving upwards. The velocity is increasing. The slope is increasing. We say that's a positive acceleration. So take a second and think about what's going on with this object. The slope of the graph, because this is position versus time, the slope of the graph tells you the velocity. So I think you can tell the velocity here is positive and large, and then it becomes not quite as big. It's still positive, but it's not as big, and here it's getting pretty small. The slope is small. So this is an object that is moving to the right, but it is slowing down. And because it is curving downwards, the curvature is downwards, we know that the acceleration is negative, okay, because the velocity is decreasing. So here's a practice multiple choice question. Take a second to pause the video and see what answer you come up with. Okay, so the correct answer for this is B. B is the correct answer. So the object is moving to the left, so if it's moving to the left, it must have a negative slope. And the only two graphs with negative slopes are B and C. So hopefully you knew that even if you weren't sure about the positive acceleration part, you could guess B or C. And if you can eliminate a couple of answers, that really helps your chances of getting it correct. So it's B or C, and now we need to know which one of those has a positive acceleration. So here, the velocity is very slightly negative. Let's say -1, and then it becomes -2, and then -3, and -4. The numbers aren't so important. It's just kind of realizing that the velocity is decreasing here. If the velocity decreases, goes from -1 to -2 to -3 to -4, that's a negative acceleration. So this is curving downwards. It has a negative acceleration. This one here, although it's negative, it's a negative large number. So let's just make up a number. Let's say this is like -5, and then it's -4, and then -3, and then -2, and then -1. This one's velocity is negative. It's moving to the left, but it is becoming bigger, going from -5 to -4 to -3. It's increasing. So think about the velocity on a number line. If you're moving to the right, that's increasing. So this has a positive acceleration. So B is the one that has a negative slope, a negative velocity. It's moving to the left, but it has a positive acceleration. All right, let's move on to velocity versus time graphs. So on a velocity versus time graph, the slope of the line actually tells us the acceleration. And here's a way to think about it. If the velocity stayed the same for the entire time, we say that it has not accelerated because we define acceleration as any change in the velocity. So here the velocity is not changing, so the acceleration is 0, and the slope of this line is 0. If you had a case where the velocity was increasing, so maybe it's going from 1 to 2 to 3 to 4 to 5, the velocity is increasing, then the rate that it is increasing, the slope of the line, tells you the acceleration. So here the slope is positive. Here in the green line, the slope is negative, so the velocity is decreasing. So on a velocity versus time graph, the slope tells you the acceleration. So not only does the slope tell you the acceleration, but there's something else interesting about a velocity versus time graph. And that is that the area under the graph tells you the displacement of the object, how far it has moved relative to where it started. And why this happens is sort of comes out of calculus. And so I'm not going to spend too much time, but I just want to kind of show you that it does connect with what you already know. If I were to find the area of this rectangle, how would I do it? Oh, there we go. So on the graph of velocity versus time, the area is the displacement. So think about this graph here. If I were to try to find the area under the graph, that's simply a rectangle. So I'm going to find the area of this blue shaded rectangle. And finding the area of a rectangle simply involves taking the height of the rectangle times its width. The height of this rectangle is 4 meters per second, and the width is 20 seconds. So if you take 4 meters per second times 20 seconds, you get 80 meters, and the seconds cancels the seconds, and you're left with meters. Now you guys probably could solve that one already. If I told you you were going 4 meters every second, how far would you go in 20 seconds? You would take 4 times 20, and you would get the answer. And so that one's kind of intuitive. But it helps to see that another way to think about that 4 times 20 is the area of the rectangle. This is basically saying that the displacement of an object is equal to the velocity times the time. The velocity is the height of the rectangle, and the time is the width of the rectangle. And of course, this equation works for uniform motion when there is no acceleration, when it keeps going the same velocity all the time. When the velocity changes, you can't use this equation to find the displacement of an object. But you can still use this idea. So here's an example problem to kind of show you that. I've got a car. Initially, it's going 5 meters per second, and it accelerates to 13 meters per second, and it does that in 4 seconds. Now, without pulling out your kinematic equations, can we find the acceleration of the car and the displacement of the car during this time interval? And the answer is yes. Let's make a graph. So if I were to graph the velocity of the car on the y-axis and the time on the x-axis, it starts at 5 and it speeds up to 13, so this is 13 right here, in a time of 4 seconds. So that is the graph that shows the velocity versus time. And the first thing we want to do is find the acceleration. Well, if you graph velocity versus time, acceleration is the slope. So to find the acceleration, you just got to find the slope of this line. And the slope is the rise over the run. So if you take the change in the velocity, that's the rise, so from 5 to 13 is 8, and divide it by the run, which is from 0 to 4 seconds, so that's 4. 8 over 4 is 2. So this tells us that the acceleration of the car is 2 meters per second every second. Okay? Mathematically, we write it as meters per second squared, but it's probably more helpful to think about it as meters per second every second. So it's going 5, and in 1 second, it speeds up 2 meters per second. So now it's going 7. After another second, it speeds up another 2. Now it's going 9. Its velocity is increasing 2 meters per second every second. Okay? So we can find the acceleration just by finding the slope. Now, how do we find the displacement of the car? Well, to find the displacement of the car, we've got to find the area under the graph, which is shaded here. And to help you see how to do this, I've actually shaded it in 2 different colors, a purple region and a blue region. So let's find the area of the purple region first, because that's pretty easy. That's just a rectangle. So that's the base times the height, which is 4 seconds, times the height, which is 5 meters. So that's 20 meters. So 20 meters is the area of the purple section. And now we need to find the area of the blue section. And this is a triangle. You know the area of a triangle is 1/2 the base times the height. So if we take 1/2 the base, which is 4, times the height of this triangle, which goes from here to here, that's 8 meters per second, we get 16 meters. And so the displacement of this car is 16 plus 20, or 36 meters. That's how far the car goes during these 4 seconds. And we didn't have to break out any kinematics equations. We just used simple geometry and the idea that the displacement is the area under a velocity versus time graph. Now there's a couple interpretations here which are kind of helpful to think about. This 20 meters tells you how far the car would have gone if it kept going 5 meters per second. Okay, so if it just kept going 5 meters per second, it would have gone 20 meters. This 16 meters tells you how much extra distance it went because it was speeding up. And so it went an extra 16 meters on top of the 20 it would have already gone, and that's how you got 36. Now just for fun, let's show how these connect to those equations, because those equations don't come out of nowhere. Figuring out how far you would have gone if you maintained your initial velocity is v0 times t. That's the area of the purple rectangle. It's your initial velocity times your time. Figuring out how far you would have gone extra because you were speeding up is this term right here. It's 1/2 the base of this triangle, which is the time, times the height of the triangle, which is the time, the base, times the slope, gives you the height of the triangle here. And so you can see this is 1/2 a t squared. And so that is our kinematic formula, which tells us the displacement of an object when it's accelerating. This term here is the area of the rectangle, and it tells you how far you would have gone if you kept going at a constant speed. And this term tells you how much additional displacement you will have because the acceleration is there, because you're accelerating. And actually, if this acceleration was negative, you'd be taking away, you'd be going less distance because of the acceleration, which was negative. So either way, this formula works. So that's a connection between the graphs of the motion and the kinematic formulas. Also, the slope of the graph, of course, is the acceleration. So if you want to know the acceleration, that's just the change in the velocity divided by time. And that's another one of our kinematic equations. I think we usually write it as v final equals v initial plus a times t, but it's the same equation. So two of our three kinematics equations we can get from this really simple idea that the velocity versus time graph tells us the acceleration, that's the slope, and it tells us the displacement, that's the area. Okay, it's fun to know, and quote to your friends, that if you graph acceleration versus time, the slope is called the jerk. And if you graph the jerk versus the time, the slope is called the snap. And it goes on and on. All right, so here's what you really need to know and understand. Okay, when we graph displacement versus time, the slope of the graph is the velocity. When we graph velocity versus time, the slope of the graph is the acceleration, and the area under the graph is the displacement. So that's kind of the key takeaway from this today, all right? The rest is just application. Now, a couple things you want to watch out for that tend to lead to confusion. Often when you're asking questions about, or you ask questions about a graph, it gets confusing whether they're asking you for the value or for the slope of the graph. So here's an example. If I say what is the displacement of the object at 23 seconds, because I am looking at a displacement versus time graph, if somebody asks you for the displacement, we are asking you to just read the value of the graph. So if you go to 23 seconds here, and you go up till you hit the graph, and you go over, that is 2. So the displacement is 2 meters. If we ask what is the velocity at 23 seconds, because you were looking at displacement versus time, the velocity is the slope. So in this case, at 23 seconds, what we are asking about is the slope of the graph here, not its value. So you need to find the slope of this section right here. So here it goes from 5 down to 0 meters, and it does it in 5 seconds. The slope is -1. Okay, so just when you're asked a question about a graph, make sure you know what graph you're looking at and whether you are finding the value of the graph or the slope of the graph at that point. All right, so here's a free response question. And you can go ahead and pause it now and try to work through it and then look at the answers, or you can kind of do it step by step with me. What we have is a car going 25 meters per second. It continues at this speed for 3 seconds, and then the driver hits the brake. And the car comes to a stop in 5 seconds. So they don't hit the brake particularly hard, but they hit the brake. So we want to do 4 things. We want to represent this motion on a velocity versus time graph. We're going to use the graph to find the acceleration. We're going to use the graph to find the displacement. And we're going to try to sketch a graph of the acceleration versus time. Okay? So here's the first question. Sketch a graph of the velocity versus time. So pause the video for a second. Maybe sketch this on a piece of paper and see if you can draw what the velocity versus time graph looks like. Okay, so here's my solution. The driver goes 25 meters per second and continues at this speed for 3 seconds. So for 3 seconds, they continue at 25 meters per second. Then they hit the brakes and the velocity decreases all the way to 0 in 5 seconds. So we started here at 3, so we end up at 8. That's 5 seconds later. It hits 0. Okay? The second question says, use the graph to find the acceleration of the car during the time the brakes were applied. So I think it's obvious that the brakes were applied during this section of motion right here. And so if we're asked to find the acceleration and we are looking at a velocity graph, we're going to find the slope. So find the slope of this section right here. And I get -5 meters per second, or meters per second squared. So the velocity decreases 5 meters per second every second until it's at rest. The third thing we want to know is, can we find the displacement, how far the car goes during this time? And so to do that, we're going to find the area under the curve. And to kind of just give you a little prompt if you want, think about this area, which is a trapezoid. Think of it as a rectangle and a triangle. Pause the video and see if you can find the area of those 2 sections and add them together. All right, here's my solution. The area of the rectangle is 25 times 3, the height times the width, which is 75 meters. So the car goes 75 meters while it's zooming along for 3 seconds. And then when they hit the brakes, this is a triangle, so it's 1/2 the base times the height. And that turns out to be 62.5 meters. And so the total displacement of the car during this time is 137.5 meters. And if we were considering significant figures, we would write that as 140 meters. We would round the two significant figures. Last question, we want to plot the acceleration of the car on a graph. So your graph will look like this. I kind of set it up with some labels and the scale already on the graph. Take a second and see if you can plot the acceleration. Okay, so my acceleration looks like this. During the first 3 seconds, the car continued at 25 meters per second, so the slope was 0. And then during the last 5 seconds, the slope was -5, so that's shown down there. And for AP Physics, we only solve problems where the acceleration is constant. So you will never have anything except horizontal line segments on your acceleration graph. If the acceleration were increasing or decreasing, that would be a problem for calculus, and we would not be doing that in AP Physics 1. So it's just going to be horizontal line segments, so that's what it's look like. All right, so just for fun, if you were to try to graph an acceleration versus time graph for this, you would need to find the acceleration or the slope of each segment. You can do that if you want. Pause the video. And here are my answers. For the first segment, the acceleration is +2. For the second segment, it's -4. For the third segment, it's positive 0.75. Then it's -3. And then the last section, it's positive 1.25. So if you were asked to sketch acceleration versus time, you would sketch a horizontal line with a value of 2 for the first 5 seconds. It would look like this. For the first 5 seconds, you'd have a horizontal line with a value of 2. That's the acceleration for the first 5 seconds. And then from 5 to 6 seconds, you would have a horizontal line with a slope of 0, and it would be at -4. So that's down here. Okay, the slope is the acceleration, so we plot the value of the acceleration here. Then it's 0.75, and then from 10 to 15, it's -3, and then from 15 to 20, it's positive 1.25. So this graph is a plot of the slope of this graph. So if you have velocity versus time, the slope is the acceleration, and a plot of the acceleration graph looks like that. Okay, 2 more questions that tend to promote some interesting discussion. How many times does this object change directions? Pause the video and think about it. How many times does this object change directions? All right, the answer is 1. I know it's kind of confusing, but right here, the velocity is positive. It's getting bigger. So let's say it's 8, 9, and then 10 meters per second. And then here, it just goes down to 9 meters per second. The car went from 10 meters per second to 9 meters per second. So it slowed down a little bit, but it did not change directions. The velocity is still positive. So as long as the velocity is positive, it is moving to the right. So it is moving to the right all the way from the beginning until this point right here. At this point right here, the velocity switches from positive, that's moving to the right, to negative, that's moving to the left. And so it changes directions right here at 13 seconds. Okay? It doesn't change direction again. It actually gets here and it stops at the end. So it only changes directions once. Okay? So it looks like it's changing directions on these corners, but they're not. When you're looking at velocity versus time, it changes directions when the velocity switches sign. It goes from positive to negative or negative to positive. Okay, another question that's often asked about graphs like this is, during which time intervals is the object speeding up? So take a second and see if you can jot down or make some marks on your screen or anything. Where is it speeding up? And remember, speeding up means that it's going faster and faster. All right, so during the first interval of time, it is definitely speeding up. It's going from 0 to 5 to 10 meters per second. It's speeding up here. During this interval of time, it's slowing down. And during this interval of time, it's speeding up again. And from here to here, it's slowing down. But now when we get on the negative side of the graph, things get a little more confusing. If something is moving backwards, so if you put your car in reverse and you hit the gas, you're speeding up. And so if you are moving to the left, if you're velocity is negative and it's becoming more negative, you're actually still speeding up. So speeding up doesn't mean your slope is always positive, because you're actually speeding up right here when your slope is negative. So here's the kind of the rule of thumb. If the velocity is positive and increasing, you're speeding up. If the velocity is negative and decreasing, you're speeding up. That's like hitting the gas while you're in reverse. If your velocity is positive, but your acceleration is negative, you're slowing down. And if you're, so like right here, if your velocity is negative, because we're below the y-axis, I mean the y-axis is negative here, this is the velocity, so we're below the graph. If your velocity is negative, but your acceleration is positive, you're slowing down. So the way that helps me to remember it is, on a velocity versus time graph, if you are moving away from the axis, you're speeding up. If you're moving towards the axis, you're slowing down. If you're moving away from the axis, you're speeding up. Towards the axis is slowing down. And now I'm moving away from the axis again. That's speeding up and then slowing down. Okay? And that's because the velocity and the speed are related. The speed is the absolute value of the velocity. So another way to do that would be to just sketch this graph and take the absolute value of it. So this section here that goes down and up, make it go up and then down, just reflect it around the x-axis, and then everywhere where the slope is positive, you would be speeding up. All right, so a way to practice this is to use a really handy app called Graphs and Tracks. And this is available free online. It's in HTML5, so it works on just about any platform. And it's really cool. So I just want to kind of show it to you and then give you a chance to kind of play with it on your own. And you can take this as far as you want to go. Let me just show you how it works though, okay? So when you go to grapsandtracks.com, you can get a practice sandbed where you can just kind of play around. And what happens is you can roll the ball, and as the ball rolls, it creates the graph of its motion right here, okay? And you can look at the position versus time graph. You can click up here and look at the velocity versus time graph. So in this case, the velocity is constant, it's not changing. And you can look at the acceleration versus time graph. So in this case, because there are no hills, this thing does not accelerate. It's zero the whole way. You can also adjust two things. You can change the initial position and velocity, so you can make the initial position of the ball maybe over here at 400. You can make the initial velocity negative, and then when you roll the ball, you can see the velocity is negative and constant. The acceleration would be zero, and the position versus time graph of the ball would look like this. It starts at 400, and it moves to the left, so the slope is negative. So after you play with that a little bit, the really fun part is to go to the challenges here, okay? And you can pick any challenge you want, start wherever you want, but what happens when you pick a challenge is, and I'll just pick challenge number 5, for example, is you get a graph, and you can see the position versus the graph, the velocity versus time graph, and the acceleration graph, and you have to roll the ball so that it matches the graph. Now, in this case, there's a positive acceleration. Can you see the little marching ants right here? There's a positive acceleration, so something must be happening to cause it to speed up to the right, and that's the inclination of the track. So you can actually grab the track here, and you can change its slope. So if I do this, and I change the height of each of the piers, so now my graph will accelerate, the velocity will increase. And so I can roll the ball, and I can see that I have the correct acceleration there. Now, if you look at the velocity graph, you'll see this is clearly wrong. I've got to do some changes. So, and you can look at the position versus time graph and see what's going on there too. So the idea is to try to use the 3 graphs to set up the track, thinking about it first, not just guessing and checking, and then roll the ball so that the motion of the ball matches the challenge that's given to you. And using all 3 graphs will help figure out exactly what's going on. Okay? So that's the challenge. See how many of those you can do? Show your friends about it, compete with them, and that'll help reinforce this idea that the motion of an object can be represented with position, velocity, and acceleration graphs, and it will help you connect the various representations to the motion of the ball.